size here. So this is currently looking through the directory with all of the pilot information. And so I'm going to open up, and I'm using, this is an Emacs, so I can look through the directory structure in the buffer here. So I go examples, 3D, X8. And so first thing, if you look at the README, it discusses all the different problems, gives you a quick description, and so we'll just run through the step 01 Dirichlet boundary condition case. So let's look at, first we'll look at our pilot app file. So this is the file that's common to all of these examples. We put that in pilot app, it's automatically read. So it contains sort of this format where we put in brackets the component name. So this is our very top level component. We don't have any parameters directly there. Then we have our journal component that this turns on stuff written to standard out. So we're going to write out stuff standard for, you know, a bunch of different types of things, and you can play around with turning these on and off. And you can actually, if you turn off all the journal output, then you can run pilot and it won't send anything to standard out. In this case, here we are in our mesh generator. Oops. Our mesh generator component. If you turn on debugging, it'll turn on very verbose debugging information about that mesh, and you can see everything that's going on internally related to what the mesh looks like and how it's stored. Then here's our reader. So we're going to read the mesh from Qubit. So the name of the component, everything that will within Pilot will begin with the name Pilot. Then there's the directory within that, which is in this case mesh input output, so mesh IO. And then the name of the component is mesh IO Qubit. And here you can turn on reordering the mesh using a common mesh reordering algorithm. Right now we have that turned off. Feel free to play with that. We give the name of the file, so mesh/box3d, box underscore hex83 hex8 underscore 1000 meters.exo. That was what we wrote out from Qubit. We have our materials, so everything comes under the problem. We have an array of materials, so we say our materials for this problem we're going to call it upper crust, lower crust, so you can call them anything you want. And then so here within our upper crust material, we have a label that's used for error messages. This ID corresponds to the node set, the block number within Qubit. We have our database of material properties. This is another just label asking, you can call it whatever you want. We have our file name for those properties. We use a spatial database file, so it's mat_elastic. We tend to you can put your suffix wherever you want. We tend to use .spatialdb for all of our spatial databases. We have the quadrature scheme. This is Lagrange cells from Fiat, so we use Fiat Lagrange. The cell dimension is 3. To change to like a quadrilateral mesh, all you have to do is change this to cell dimension to 2. You use TETS, then you would use Fiat Simplex, and then similarly cell dimension 3 for TETS, 2 for triangles. Our PETSI solver parameters, and Charles, can you the general addition is the same as the one specified for Qubit. So the block number in Qubit should match the ID here in Pilot. And we can look and see, we can look when we run the example, we can see what happens if they don't match. So PETSI, here's our PETSI solver parameters. we suggest looking through the manual. Some of the things to point out, you have your preconditioner type. Generally using ASM for small problems works pretty well. Our convergence tolerances, maximum number of iterations. We're going to monitor what the solver is doing. We want it to tell it why it converged. And then when we use a nonlinear solver, it's sort of the same information. So that's for Pylith app. Let's look at step 01. Again, a bunch of comments at the top. Here's our first sort of component here. We're doing a time-dependent problem. Formulation, the default formulation is implicit. So what is how much time? We're going to do 0 time. That means we're going to do a static simulation. We still give it a DT of an appropriate time step. This is important for non-dimensionalizing values, especially in quasi-static simulations. So it's good to just specify a time step even if you're doing a static simulation. Here's our boundary conditions. We have X positive, X negative, the bottom. Here was some testing for Matt, so please ignore that. We should take that out of our test cases here. Implicit time stepping, our output is going to be over the domain and subdomain. And then an output over the subdomain is a special output type output solution subset. It knows how to extract sort of for a boundary surface, and it is limited to boundary surfaces at this point. Here's our boundary conditions. They're going to be Dirichlet boundary conditions. That's the default. You'll notice that that's why we don't have to specify it. The default is also 0 displacement boundary conditions. So all we're going to say is what degree of freedom we want to constrain. So the X degree of freedom is 0. Y degree of freedom is 1. So we have that on and we're going to constrain the initial displacement. So there's a database initial, and see the manual discussion for time-dependent boundary conditions for the various databases that are available. Here's our file name for where that spatial variation in values are coming from. Very similar to the -X space, and then on the bottom, it's going to be the Z degree of freedom. And then output, we're going to use BTK output. So basically, we're giving it the names of the file names, and then for our ground surface, we say, well, how are you going to find the ground surface? All right, so this is the name of the node set from qubit. So face Z positive. For the volume, we want to average the values over the quadrature points. So we use this cell filter. It's called cell filter average mesh. And the mesh corresponds to the fact that this is over the volume. So it's the mesh, not the submesh. So let's run this problem. And so I need to get a terminal window here. Emacs, stop sharing. Okay. Show that terminal window. So I'll go to 3D hex 8. And then bigger. First thing, let's just run step 01.cf2. So you see stuff written to the standard out. So let me scroll up and show you the first increase the width of my screen. So this is a bunch of logging information, and I go back up to the top. And so if I get back up to the very top, so there's a couple warnings. These are things you can ignore. You'll see these just talking about some things that are already existing. This is sort of the main thing we're going to do. First, we initialize PETSI. Then we're going to read in the finite element mesh. This tells you the exact, these are those journal commands or sort of journal outputs. So it actually tells you what line of what file where it was when it was telling you this information. It says how many vertices were read. It says how many cells and the number of blocks. Those are the number of node sets. which node sets it found, what the ID was, and how many nodes. Now it's going to pre-initialize the problem, pre-initialize the materials. It's going to initialize the quadrature information, so it's saying in my reference cell, here's my vertices, here's where my quadrature points are, here's my numerical quadrature weights, here's my basis functions evaluated at the quadrature weights, basis function derivative at the quadrature weights. And it does that for both the two different kinds of materials. Come down here, I'm going to see it says I'm adding an elasticity integrator for the lower crust material, pre-initializing the boundary condition it already added above the integrator for the upper crust material, pre-initializing, now it's done initializing, so it's going to start initializing the problem, initializing the integrators, initializing the constraints, setting up the solution output, creating some fields, creating the Jacobian matrix, so our sparse matrix. Now it's initializing the solver. Now it's going to solve. So here I'm in the various parts. It's reintegrating the Jacobian operator, solving equations, and I'm using iterative method. So here's the iterations. You see the residual norm decreasing nicely. So in 20 iterations, it's converged. It tells me why it converged due to relative tolerance. And it says, okay, I'm going to finish up. I'm writing solution fields. I'm finalizing. Now I'm finalizing PETSI. And so here's all the PETSI performance information. It told me it took 0.4 of a second. It had 66 objects. Here's an estimate of the number of floating point operations it did, how many floating point operations per second, how much memory in just the PETSI objects. So this is not everything. If there are any MPI messages, it breaks down all of how long it took for the various stages of the solution. So when you want to really try and improve the performance, you can look and sort of see where it spent its time, where there might be bottlenecks. In this case, the solve, pretty much the setup took, in terms of total time, about 60%, solve only 6.4, writing output took nearly 10%. You notice we have a warning down here that I was running a debugging version, so the performance would generally be 2 or 3 times faster if you use things like the binary, which have the debugging turned off. And this is very specific information about how much time, how many times routines were called in the logging information. If you have, and also down here at the bottom, it has information about how the PETSI part was built. And another thing to note is at the end, it says, here was a PETSI option you selected but didn't use. And so this is very handy to check. These are all SNES, so that's the nonlinear solver parameters. If we were solving a linear problem, we didn't expect it to use a nonlinear solver, so it's fine that these options were left. But if you misspell something, it'll usually show up here as an option left that wasn't used. So we had a question about using or sort of matching IDs. So I'm going to go over here and I'm going to change in the pilot app file, I'm going to change the ID of material 1. I'm going to say ID 7. So say we happen to have a wrong ID in our material problem. And okay, so here we go. When we run pilot, we get an error. It says, so the first thing you'll notice is that the error message, not only does it just give you an error message, it gives you a stack trace of where it was in the application. And so it was, I can see the most recent one is here at the bottom. So it was running a routine called check material ID. So we actually do verification of these material IDs. And here's our actual error message here. So it says material ID 1 for cell 0 does not match the ID of any available materials or interfaces. So it looked at a mesh, and said, I have cells that have an ID of 1, but you didn't specify any materials in your parameter files for a material ID of 1. And so we can go back in here and I can correct my ID to 1, and then go over here, and if I run again, everything runs through. Now let's say I add in, let me quickly add in here let's see what happens if we add in an extra material. So I'm just going to call it over, I just cut and pasted an extra material in here. I need to add it to the array. So let's just say I think I have 3 materials. I have material ID 1, 2s, and 3s, but my mesh, I forgot to create a mesh with 3 materials. Let's see what happens here. Aha, so now I have a different error message. It's still in the same routine, check material IDs, but now my error says no cells associated with ID material 3. So it's our parameters that said you gave parameters for a material with an ID of 3, but when I look in the mesh, I don't see any cells that have a block ID of 3. And so it says you have no cells with material ID of 3. So if you forget to add in a material into your mesh but have it in your parameter file, or vice versa, Pylith will actually detect that and give you an error message. Let's say I have the wrong, let's say I think I use the wrong dimension of, say I tell it that I want 2D quadrature, but yet I'm running a 3D problem. So now I get a different place, a different error message. I'm still in a material-related routine. And now it says I have my quadrature scheme for material, upper crust material, and the mesh are incompatible. So my quadrature material was a dimension 2 in 3 dimensions with 4 corners. So that would be a quad in 3D. I look at what my mesh has 3D and has 8 corners, so it's a hex cell. So it's telling you that your quadrature scheme was incompatible with your mesh. So we're trying to detect most of these problems up front, and of course if I fix those I get back to my original problem runs through. Any other questions at this point? Okay, let's quickly, we may have another question. Okay, don't see it showing up yet. I'll switch over to pair view so we can visualize this.